another speaker, namely Les Johnson, who is principal investigator of 2 interplanetary solar sail missions at NASA, George C. Marshall Space Flight Center, of course in Huntsville. The first, the Near-Earth Asteroid Scout, scheduled for flight in 2020, will use 925 square-foot solar sail to propel a small spacecraft to rendezvous with an asteroid. And the second, the Solar Cruiser, will demonstrate the ability of an 18,000 square-foot solar sail-propelled spacecraft to perform scientific observations of the Sun when it flies in 2024. Please welcome Les Johnson.
Good afternoon, thanks. I was told to be on standby in case any of the speakers dropped out, and we had one do that. So here today I'm going to give you an update on what's going on with solar sail propulsion within NASA and in the community in general. If you were here yesterday morning, you heard Greg Matloff give quite an excellent summary of the history of interstellar propulsion research. Part of that is happened when I worked with Greg, and he came to NASA Marshall. But solar sails and their cousins, laser sails, play a big part in that. And there are 2 directions you can go with solar sailing to the stars and laser sailing to the stars. You can go the approach that the Breakthrough Starshot has chosen, which is really high-power lasers and very small sails. Or you can go the more, quote, traditional interstellar approach that was pioneered by Dr. Robert Forward and Greg Matloff and others, where you go to ever larger, lighter weight sails as opposed to ever smaller sails with really high-power lasers. The path that we're currently on in developing solar sail propulsion is really to answer near-term science needs and transportation needs in the solar system. But as we do that, we're developing solar sails that are more along the lines of the Robert Forward, Greg Matloff path, which are to the ever larger, more capable sails. And that's what I'll tell you about here today. So let's just quickly review how a solar sail works. Talking about swimming upstream, solar sails can do that. I'll describe how that happens in just a moment. But a solar sail is just a big, lightweight reflector. And all you're doing is putting it out in space, deploying a large, lightweight, thin film reflector, and taking advantage of the photon momentum. Photons have no rest mass, but they do have momentum. And when they reflect from the sail, if you imagine light waves as little particles bouncing off, that's exactly what they do. The light bounces off the sail, and the momentum that the photons carry pushes on the sail, and it reacts against that. For those of you that are quantum mechanics interested, the photons are slightly redshifted. You're conserving energy in this, in that you're imparting some of the energy of the photon to the sail. So I'm going to pass this around. This has been held by thousands of people. This is a piece of solar sail material like we're actually going to fly. If you try to tear it, you can. Please do not try. But just by handling it, you'll see basically how lightweight it is. It's about 3 microns thick, and this is actually the very same material. This is very wrinkled. The actual pristine sail is pretty reflective. This is one that hasn't been handled as much, and it's on a backing to keep it flat. So when we deploy our sail in deep space, we're reflecting light. And if you change the angle with which the light reflects from the sail, you can steer. So if this is my sail, and the back of the room is the sun, and the Earth weren't moving around the sun, and we just pop this out into space magically, it would be propelled away from the sun radially. Most people get that. But the Earth's in orbit around the sun. We've got orbital velocity. Any rocket we launch from the Earth, which is what we have to get the sail out of our gravity well, also has orbital velocity. So the sail is actually moving around the sun. So it's got a component of its velocity that's tangent to the circle of the orbit that it has, right? So if you take your sail and you tilt it like this, you can actually reflect the light so that the net thrust vector is not radially outward, it's at some other angle, and a component of that thrust vector is in the same direction you're already moving. So what happens when you accelerate in the direction you're already moving? You move faster, and your orbit spirals out from the sun because you gain energy. Well, you can also tilt the sail the other direction and decelerate and lose energy, and the sun's gravity starts pulling you in, conservation of energy. Well, you also have at that point the inverse square law working for you, which means as you get closer to the sun, the intensity of sunlight pressure on your sail doesn't just get bigger linearly, it gets bigger as the inverse square of the distance. And what that means is if I go halfway to the sun, I don't get twice as much thrust, I get 4 times as much thrust. So a solar sail actually can work quite effectively going toward the sun as well as away from the sun. So anywhere the sun is shining in the solar system, you can propel using a solar sail and do that quite effectively. And that's why it's of interest to the space science community. Believe it or not, in the last 15 years, we have had a golden age of solar sail flights. The NanoSail D, flown by NASA at the Marshall Space Flight Center, was a 10 square meter sail, flown in Earth orbit on a 3U CubeSat in 2010. The Icarus sail was a Japanese solar sail that also flew in 2010 in the Japanese Skunktus. They flew a much larger sail in interplanetary space, demonstrated thrust vector control of that sail, and flew close to Venus with it. It was an in-space demonstration of a solar sail, quite successful, called Icarus. The light sail from the Planetary Society was based on the NanoSail D design. As the Planetary Society was designing their light sail, and the folks were doing that, they too were taking advantage of the CubeSat revolution. And we have a data sharing agreement with the Planetary Society, so we've looked at each other's designs. And theirs is essentially an enlarged version of what we flew in 2010. It was 32 square meters. They flew that successfully first in 2015 and again this year. In between there, the Canadians demonstrated a small sail. The Europeans, with the University of Surrey, demonstrated what they called inflate sail, which was a 10 square meter solar sail, also in Earth orbit, CubeSat. There's one in space. There are two in space right now. There's the LightSail 2, which is deployed, and you've seen data from that. There's also one from CU Aerospace, which is a blade sail, 1 meter wide strip, 20 meters long, deployed on a CubeSat launch about several months ago, and it has not yet deployed. It turns out there's a orbital debris risk mitigation. They have to get to a low enough altitude where they can deploy, and they aren't going to pose a risk to other satellites. So that hopefully will deploy a little bit later in this year, and we'll have more sail data from that. The two I'm going to focus on today are the Near-Earth Asteroid Scout and the Solar Cruiser, both of which I have the privilege of serving as the principal investigator for. NEA Scout is a full-flight sail, 86 square meters, and the Solar Cruiser is a big leap in size. It's over 1,200 square meters, 1,200 square meters. Our goal is 1,600 square meters. And those of you that don't think metric, that's about 18,000 square feet, so it's quite a large sail. Let me tell you a little bit about NEA Scout. NEA Scout is loosely based on our NanoSail D design from 2010, but it's an order of magnitude larger. Our goal was to design a 6U CubeSat form factor spacecraft and increase the sail size by an order of magnitude. We didn't quite get there. We got to 86 square meters. We are packaged in a CubeSat volume, but this is not a CubeSat. This is a fully functional interplanetary spacecraft manufactured by NASA at JPL. It's very similar to the Marco, which they flew successfully to Mars. Has the same flight avionics, computer, main subsystems, but instead of a conventional propulsion system, we've taken up the middle part of the spacecraft to put our solar sail, which takes up about 2 of the 6U in the spacecraft. We're going to fly as one of 13 CubeSats that will be deployed on the first flight of the Space Launch System when it flies later in 2020 or early 21. After the Orion spacecraft is kicked off to go around the moon, these 13 CubeSats will be kicked out, including the Near-Earth Asteroid Scout. We'll deploy our solar sail in the lunar orbit vicinity, check out, make sure we know how to steer and to fly, and then we're on our way to an asteroid. We have about a 2.5-year cruise. We're carrying a camera in 1U, and the camera is to do close-in reconnaissance of a NEA and send the data back with our onboard telemetry system. So the solar sail is the primary propulsion after Earth escape to steer and do a close flyby of an asteroid. Now this is to show you that the hardware is all together. In fact, the spacecraft is essentially complete. It's being integrated in Huntsville as we speak. We'll have it integrated before Christmas. We deliver it to the launch site next spring. This is a picture of my team at a full-scale deployment of the sail. It all came out of this little 2U spool right here, which you can see in the center of the table, and this is the fully deployed sail. It uses booms. We have 4 7.3 meter booms. You can see them here that are coiled up, also in the CubeSat, and we have a motor that pushes them out, actually restrains them from automatically deploying. The strain energy in these booms is pretty incredible. If we were to just let go of the coiled boom, it would basically deploy itself. And it would do so fast it would probably destroy the sail. So we actually have a motor to slow down the deployment and have a more controlled deployment. The whole deployment of the sail will take less than a half an hour once we're in space. The mission overview of NEA Scout as we launch, we check out the spacecraft first, make sure it's going to work. Everything's functioning, that we can call home, that we're generating power. We then go into orbit around the moon in a highly elliptical orbit. We deploy our solar sail. We spend a few weeks there in checkout, and we're really doing that waiting on the phasing with the asteroid to be right, to spiral out and have the best trajectory to do our flyby. Because we're exactly not certain yet about exactly when we're going to launch, we have several candidate asteroids we can visit, and the beauty of a solar sail is we're rather immune to launch window, in that if you were picking a specific asteroid with a conventional chemical system in this small a footprint, you'd have to launch exactly on time, or you wouldn't have a prayer of catching it because you wouldn't have the delta V you need to get there. With a solar sail, it's a matter of varying the trip time. So we can go anywhere between 1.5 to 2.5 years. And there are lots of candidate asteroids of interest. So we will fly out. We'll use our onboard camera to do the final target acquisition. We'll fly within 1 kilometer of the asteroid, essentially matching velocity with it, slowing down to about 20 meters per second relative to an asteroid moving at 20 kilometers per second. We'll do our science, and here's where a solar sail gets so cool. If we don't get all the data we want, we could loop back and come around and fly by again. It'll take about 6 months for us to do that, but as long as the sailcraft is functioning and nothing has failed mechanically, we can keep going because we don't require no stinking fuel. Okay? And if there are other asteroids of interest, we might have targets of opportunity if the spacecraft stays alive. We expect the limiting factor on the lifetime of the spacecraft to be the spaceflight electronics. They're going to get their lifetime radiation dose and probably crap out on us after about 2.5 years. But if they're still functioning, we could in principle keep going. So this team has finished development of the sail. We actually finished it a year ago. And a year ago, we turned in a proposal to NASA's Science Mission Directorate, which called for something called a mission of opportunity. And what that means is they have a mission that's going to launch in October of 2024. It's called the IMAP. It's a science mission. And it's launching on a very large rocket that actually happens to have extra payload mass and volume in the fairing. So they're attaching what's called an ESPA ring, which is basically an adapter that goes in there to which the spacecraft is mounted, and you can mount other smaller spacecraft to fly with it because you have extra volume and extra lift capability of the rocket. So they said, hey, we need new technologies that are going to enable future missions to study the sun. So go look at all the studies we've done over the last 20 years and tell us what technology we need to demonstrate in space so that after it's demonstrated, we can do some new science missions that we currently can't do once we have this capability. Well, the reference document for that is something called the Heliophysics Decadal Survey, which is basically done by the National Research Council that says, here are all the priorities for space science for the next 10 years. Well, I'm just saying, if you go back and look at that document, you'll find that there was a white paper written in 2010 that went into the document that tells them all the great things they can do with solar sails. And I just wonder who might have happened to write that document. But anyway, we actually wrote our proposal. Pretty stiff competition. There were a lot of proposals, many different technologies. We were the only solar sail proposal that I'm aware of that went in. Other proposals were new types of instruments, new types of measurement techniques. They picked us. We found out in August is when I got the call from NASA headquarters that the team had been selected to go through a Phase A. We have a down select next year to make sure we can actually do what we say we're going to do. We get through that hoop, we fly in October of 2024. So Solar Cruiser is going to be a much larger sail than the NEA Scout. It'll be the same basic architecture, big booms, big sail, 3-axis controlled. We are going to fly, after we eject from the launch vehicle, the ESPA ring that I told you we're attached to, we're going to fly to the Earth-Sun L1, which is a loosely stable gravitational area where you can put a spacecraft, and with a minimum amount of propellant, it'll stay there always on the Earth-Sun line. But we're going beyond that. We're going to go sunward of L1, quite a distance. And we're going to use the continuous thrust of the solar sail to adjust our orbit continually so that we're always remaining on the Earth-Sun line, even though we're not in a stable orbit. We're creating our own halo orbit with the sail. After we demonstrate that, we're going to tilt the sail, and instead of accelerating and decelerating, we're going to crank our inclination out of the ecliptic and do some science observations with an onboard chromospheric imager being developed by the High Altitude Observatory to study the sun and show that the sailcraft can actually act as a stable platform for optical imaging of the sun. So, I want to thank all the investments that have been made in solar sails over the last 20 years. This is not an exhaustive list within NASA, but it's a pretty extensive list. And the heritage of the team that's building Solar Cruiser goes all the way back to the team that built some big solar sails back in 2004 and 2005. From there, we learned how to build these sails. We built the NanoSail D. That led indirectly to the Planetary Society's activities, and it led directly to the NEA Scout, which has led to Solar Cruiser. Our contractor partners have gotten investments from the Space Technology Mission Directorate to build big booms, big fabric for the sail. And one of our contractors building the solar sail happened to also build the sunshade for the James Webb Space Telescope. So we've got a team that's pretty experienced in building large, lightweight deployables. Here's what the sail looks like. It's big. Think about 40% the size of a football field big. It's going to have these composite booms, which are pretty lightweight, which will deploy the sail. We're going to affect attitude control with reaction wheels. And we also have an innovative electro-optic thin film that we're embedding in the material, which you can vary the reflectivity of to get torque on the sail. If your reflected light and photons hit the sail, they essentially give twice as much thrust as if in comparison to like a black absorptive material where the photon is absorbed and you only get half the thrust. So if you're looking at this big sail and you want to tip or tilt the sail and you don't want to do that with a moving part really, if you can make this part of the sail not quite get as much push as this part, you can affect a torque on the sail and tip and tilt the sail. We're going to do that without as many moving parts by having this variable reflectivity coating. So that's pretty exciting, and I think that's essential to building the larger sails that we have to have for doing science. We're carrying we were carrying a coronagraph. We now have changed that over to a chromospheric imager. I won't belabor that point. Ball Aerospace in Boulder is building our spacecraft, to which the sail will be configured and mounted to. So we have a pretty high TRL flight-proven spacecraft that we're flying on. We do have a one-year mission with a one-year option. This is the timeline that we proposed, and we're refining it this year. But basically, by the time we finish year 2 of the mission and write the papers, I'll be 65. Nice coincidental timing. So, after the first year, we have a science enhancement option in that if everything's working well and we don't need no stinking propellant, we're going to continue flying the chromospheric imager and returning some science for the Science Mission Directorate. So, why are people interested in solar sails in the near term? The near term are things like advanced warning of solar storms, which is a whole talk in and of itself. But the bottom line is right now for solar storm warning, NOAA, the weather people, also provides space weather forecasts. And they have a spacecraft sitting at Earth-Sun L1, which detects the particle and field measurements that come from a solar storm approaching the Earth, which is moving slower than the speed of light. They send a radio signal home that says, batten down the hatches, we have a solar storm coming. And about an hour later, the radiation storm arrives at the Earth. Okay? They want to increase the warning time. An hour is not a lot of time for the utilities and the spacecraft operators to get ready for that. If you fly sub L1, like we'll be doing with Solar Cruiser, and you take our chromospheric imager off and you put these same particle and fields measurements, you have an operational space weather system that could double the warning time for space weather events with a copy of Solar Cruiser, not a bigger sail. We could do that right away. There's also going to be an enabled capability with a sail that we will demonstrate scalability to, which is only a few times larger than Solar Cruiser, and that's something called a pole sitter. A pole sitter would allow you to not orbit the Earth, but hover over the Earth's North Pole or the South Pole, co-orbiting the Sun, with the sail used to counter the Earth's gravity where you are. So in other words, if you put this over the North Pole, it's not circling North Pole, South Pole. It's acting like a geostationary platform at the equator, hovering over the North Pole. And if you had a child with you and dropped a penny, it would not stay in orbit. It would fall to the Earth. Okay? So your sail is actually hovering there. This is a capability that is not currently available with any propulsion system, and a solar sail would enable you to do this. High inclination solar science is really the killer app for the people who are funding Solar Cruiser. They are, I don't know if you're aware of this, but we really don't know what's going on at the north and south pole of the sun. We orbit the ecliptic plane around the equator of the sun, and we're looking up at this big 105 Earth tall object and modeling what's going on in the sun, and we don't really know what's going on in the north and south pole. There was a mission called Ulysses that gave us about 90 days before it no longer was able to see it, and it had to go out to Jupiter and do all kinds of flybys and didn't really enter a solar polar orbit. And this science community is extremely eager to put a spacecraft in a solar polar orbit so they can do extended observations of the north and south pole of the sun, and we will enable that with Solar Cruiser. I mentioned we're going to be cranking out of the ecliptic. Well, the follow-on mission, after we demonstrate the technology, if you go into half an AU with a sail not much bigger than Solar Cruiser, where you get 4 times the thrust, remember the inverse square law, that we get at the Earth, you can slowly crank your inclination out of the ecliptic plane and go into that solar polar orbit to enable solar polar imaging. And that's really the killer app of why we're being funded, is to enable that. But my real motive is to go to the stars. So here is a variation of a roadmap that will look familiar to several people here. You know, I work for the government, so when people are disgusted with their government, they say those darn bureaucrats. Well, those darn bureaucrats build roadmaps. And similar to the roadmap that we're going to be building later this week for laser beamed energy propulsion and high energy density propulsion. And this roadmap was put together about 20 years ago of how we go from a 10 square meter solar sail methodically to the size sails we need to go to the stars, which are on the order of 10 to the 6 square meter sails, square kilometer sails. And I'm pleased to report that we've taken a little longer than we thought it would take, but we are now approaching step 3. We started out with the NanoSail D, 10 square meters. NEA Scout flies next year. It's essentially 100 square meters. It's about 86 square meters. We could have packed in 100 now that we have the hindsight design experience we have. We could have packed in a little bit more sail, but we didn't. We were being a little bit more conservative. You have the greater than 1,000 square meter Solar Cruiser sail, which we're now in development of, which will fly in the mid-20s. And from there, you can jump right up to the 10,000 square meter sail, where you can actually start thinking about laser augmentation of some of these sail systems. So I don't tell you right now that we know how to build anything bigger than that, but I will tell you that the engineering team that we have didn't know how to build Solar Cruiser until we finished NEA Scout, and we didn't know how to build NEA Scout until we finished NanoSail D. And we seem to be on track for mastering the next order of magnitude larger sail every 5 to 8 years. And I can't promise that trend will continue, but it sure looks promising, at least up to about 10,000 square meter solar sails. So it's pretty encouraging. I never thought when I was first dabbling in interstellar stuff with Greg 20 years ago that we would be at the point where we are today. We've actually made progress, and I'm really excited to report that to this community. And the pathway is there. There are no plans in firm shape to go beyond this multi-thousand square meter sail, but I suspect after we're flying those and we're doing solar polar orbiters and we're doing solar storm warning, people are going to look at even more challenging missions and take us to the next level of sail development. And with that, I'll stop and take questions.
So you were talking about that roadmap development. So instead of Moore's Law, did we just see Johnson's Law be dubbed?
Ooh, how cool would that be? Well, Joe, seeing you stand there makes me think of something, though. You know, when I started in this work, and we looked at what the material requirements would be for this really big sail, it was unobtainium. It really was. There was nothing that had the strength and the thinness, the lightness ratio that you could build a sail that big and even have a prayer of having it hold together. But in 2004, there was a discovery of this material called graphene, and it turns out that graphene has the material properties, except for the reflectivity. You have to dope it, as Greg said. And what got me interested in graphene was a paper by Greg Matloff, where he was the first to realize that the graphene might actually enable us to do that. And so what is also way cool about this roadmap is we went 20 years ago from here, where this had to be made out of unobtainium. We're now on step 3, and we have the material for the kilometer scale sails. So that is way cool. We just don't know how to make it big. Right now, graphene's in very small pieces. So we've got to learn how to engineer that.
Well, it's a good thing I'm talking about graphene photonic sails tomorrow morning, then.
Good thing. Good thing.
Hey, Les, thanks for all the citations, as always. Yeah, I have a question based upon a paper we co-delivered at an earlier version of this workshop on NEA Scout.
Yes.
And the possibility, which appeared to us, is that it will be possible to pioneer the sundiver maneuver after asteroid exploration was accomplished with this vehicle. Not to get any science from the heliopause, but to show that we can control something close to the sun. Has there been any further thought about that?
We're going to probably be out of range where we could actively control the momentum on the sail, Greg. I think if we had a more powerful communication system, one that would allow us to get a little bit higher data rate, we might be able to go in close enough to what Greg's referring to is he did some calculations that said if we went, it wasn't quite Mercury orbit, I think it was further out than that, that the solar photon pressure would give a solar system escape, and that we might be able to send this little craft on its way out, even though we'd never be able to talk to it after it got, a little bit past the Earth. But I really suspect we aren't going to be able to have active control of the sail long enough to give it the trajectory we need to do that, which is a real disappointment.
Yeah. Thank you.
Because, in my science fiction half, my DNA is going to be on this spacecraft, and I was looking forward to the alien race cloning me. But it's just not going to happen, I don't think, from NEA Scout. Now, maybe from Solar Cruiser.
Maybe so.
Yeah.
Hi. I have two questions, but the first one's fast. What coding are you using to change your reflectivity? And then the second question is, what is the advantage of just scaling up these solar cells as opposed to using an array of smaller solar cells that we feasibly know how to make, as opposed to overcoming the technical challenges of making 1,000 and 10,000 square meter solar cells?
Okay, I'll answer the second one first. Newton's law, F equal ma, sunlight pressure at any given distance over a certain area is constant. So if you want to have a large acceleration, you have to have a low mass. And to get that large acceleration from a sail with low mass, you need to reflect as much light as you can reflect from the sun. And so we're really driven to build these really large, lightweight reflectors so that we can have an appreciable acceleration with a mass that's useful. People often ask me, Les, looking at your roadmap, what's changed in the 20 years in the near-term sails, not the unobtainium to graphene, but the near-term sails that's enabled these missions to be feasible today where they weren't feasible 20 years before that. And it's not the material from which the sail is made, and it's not necessarily the booms. It's been the revolution in the reduction of spacecraft mass. We now actually have spacecraft masses that are light enough that you can build a realistically sized sail to do these missions. So the reason you don't want to do a bunch of small ones like, say, NEA Scout. NEA Scout, if you want to do asteroid exploration and you want to do multiple asteroids and if you're an asteroid mining company, I've got a deal for you, right? Because most of the cost of NEA Scout went into the design and development. The recurring cost, we could crank out another one for under $10 million. Fully functional interplanetary survey spacecraft for under $10 million. And so I think there is utility in the smaller sails, but if you want to do a suite of instruments which are fairly heavy, that requires a spacecraft which can provide their power and hold them, which drives you to a bigger sail in order to get the acceleration you need to be able to do the mission.
So this is an easy one. It kind of follows on. What aerial densities are you hitting, and what aerial densities are you projecting on Johnson's law?
Johnson's law. I love it. With the aerial densities, we're in the tens of grams per square meter, dropping down to less than 10 grams per square meter. I have kind of switched what I like to characterize as sail performance from aerial density, however, to the characteristic acceleration, because it gives you more of a system level feel. And it lets you add up not only the weight of the sail and its area, but its thrust performance as a system where you've attached your big heavy spacecraft to it. Our characteristic acceleration for Solar Cruiser will be 0.17 millimeters per second squared, of that order. NEA Scout is 0.07 millimeters per second squared. And with this same sailcraft and a slightly lighter bus, we can hit 0.3, which is just awesome in terms of performance. So, yeah. All right, very good. Thank you. Where's my sail?